Welcome, kiddos. To start our conversation about the calculations involving acids and bases, we're going to be doing what I call the 4-beaker problem. I have here 4 beakers, a strong HCl acid, a weak acid, acetic acid, a weak base, ammonia, and a strong base, calcium hydroxide. Now, they are all 0.023 molar because that's what I can get with saturated calcium hydroxide. That's the most concentrated we can have. So they're all the same molarity. Now, you notice that they're different colors. You would expect an acid to be clear and colorless. But what I've done is I've added universal indicator, a couple of drops of universal indicator. An indicator is a dye that changes structure with pH, and as it changes structure, it changes color. Remember, structure determines function. So over here we have our strong acid is kind of an orangey pink maybe. Acetic acid is getting more pink. I want you to write those colors down on your beakers in your notes. My ammonia is purple, and my calcium hydroxide is blue. And as you can see in this picture, you see a whole range of colors available for your pH scale when you're using universal indicator. You're familiar with phenolphthalein, which is colorless, and then pink, and also litmus paper. And what we're going to do in our next segment is we're going to calculate the pH of the solution in each of these beakers.
We will start our conversation by looking at our strong acid HCl. So we have 0.023 molar. Now, since we did not add volume to volume, we don't need to do a dilution here. And since it's a strong acid, it's a stoichiometry. Don't forget that H3O plus and H plus are symbolic synonyms. Now, our shift, since it is a strong acid, will be 100%. That's the definition of a strong acid, is it ionizes essentially 100%. Now, I'm doing the long way here. In just a moment, I'm going to show you a shorter way. But no matter which way you do this, you need to show me that mole ratio, is that you know that it's a 1-to-1 mole ratio. No assumptions. All right? So, of course, I have none of that left because it went 100%. And I have 0.023 molar H3O plus and 0.023 molar Cl minus. pH is equal to minus the log of my H plus or H3O plus. Whoops. And I get 1.64. Now, a quick word about significant figures here. I have 2 significant figures in my original, and when you take the log of a number, it's only the numbers after the decimal point that are significant. That number in front is telling us magnitude. So the numbers afterwards are significant. Now, certainly a much simpler way. Remember, DSE is a surefire way to get your mind going, but it's not always the shortest way. You certainly could have done a very simple stoichiometry. I've got this many moles of HCl per 1 liter. I'm going to multiply by ions within 1 mole of H plus for every 1 mole of HCl, and you would have had the same number. Or, honestly, in this case, I would accept this. This, to me, tells me you recognize that there's a 1-to-1 mole ratio here. So, for me, that would be enough work, and it's certainly a lot less than this up here. But pretty quickly, you're going to be relying on that SSS chart to get us into our equilibrium. So, let's take a look at our strong base for this video, and then we will cut it short for this one. Let's look at our strong base. I intentionally chose one that had 2 hydroxides. Now, because of that, that limited my molarity here, but it turned out to be work quite well. Again, no dilution. We're simply looking at what's in that beaker. Molarity is intensive. It doesn't depend on the amount. So I'm going to pop that right in here. Again, the SSS is a little longer, but I want you to become familiar with this, and I think you'll see why by our next video. Now, this time is one of the few times in acid bases that you'll actually have something other than a 1-to-1 mole ratio, and that's right here. And that's because we get 2 hydroxides for every 1 calcium hydroxide. So this is 0, and again, a strong base ionizes 100%. This is 0.023, and this is 0.046 molar. Now, this is my OH, so what I'm going to do is I'm going to calculate POH and then get to pH. Now, you could just as easily go from OH minus to H plus to pH. I just think it seems like fewer keystrokes when I do it this way. So I'm going to get my POH, and that's minus the log of 0.046. And I get 1.34 for my POH, but you can't stop here. The question is asking what is our pH, so it's 14 minus that. Whoops, that's a minus, sorry about that, 3,4. And so I get 12.66. What we need to do then, what I want you to do, is look at that universal indicator chart and see if the colors from our Beaker experiment match up to our pH of 12.66. Now, before I leave this, I do want to show you that there, would certainly be a simpler way to do this, but DSE, Doc Saves Everyone, really gets your mind working when you're not sure how to start a problem. Okay, so I've got calcium hydroxide. We're going to do ions within, which we did very early last semester. I get 2 moles of hydroxide for every 1 mole of calcium hydroxide that ionizes. And that is sufficient for your work here. And it's a lot less than filling out that whole chart. All right, just make sure you show me that mole ratio. So, talk to you soon, kiddos. Until then, this is, as always, signing off.